Good day, I am Fatima May Arilia together with my partner Gemma Tolentino, presenting our paper entitled Adsorption of Diclofenac in Aqueous Solution using Chitosan-Impregnated Biochar Beads from Pineapple Leaves. Diclofenac, a widely prescribed non-steroidal anti-inflammatory drug, is increasingly recognized as a persistent environmental contaminant. Its widespread use and its resistance to degradation have led to its accumulation in aquatic and terrestrial ecosystems. Conventional wastewater treatment processes are often ineffective in removing diclofenac, necessitating the development of alternative, efficient, and eco-friendly technologies. Adsorption, a well-established technique, emerges as a promising approach for the removal of organic pollutants like diclofenac. The choice of adsorbent is crucial in determining the efficacy of this process. Therefore, chitosan, a naturally derived biopolymer, has garnered significant attention due to its excellent adsorption properties, biodegradability, and non-toxicity. Its unique structural features and functional groups enable it to effectively bind with a wide range of pollutants, including diclofenac. Different studies have explored the biosorbent capabilities of chitosan. For instance, Ranjbari et al. Employed chitosan beads impregnated with novel aliquot 336 to remove anionic azodyes. Similarly, Lu et al. Utilized chitosan beads impregnated with nanoiron oxides for the removal of hexavalent chromium from aqueous solutions. While these studies demonstrate the versatility of chitosan-based adsorbents, the application of chitosan-impregnated biochar beads derived from pineapple leaves for diclofenac removal from aqueous solutions remains unexplored. The objective of this study are as follows: to synthesize and characterize the chitosan-impregnated biochar beads and assess its potential in removing diclofenac from simulated aqueous solutions, to identify the influence of different factors in the biosorption capacity of the amalgamated biosorbent beads such as biosorption temperature and biosorbent dosage. Lastly, to determine the adsorption mechanism of biosorbent material using Langmuir and Freundlich isotherms.
This study looks forward to contributing to several fields in several ways. First, we aim to join and support the cleaner and greener engineering movement through the reduction and recycling of wastes such as the pineapple crown leaves. Aside from being cost-effective, pineapple crown leaves are also an accessible material that can be seen almost everywhere. Aside from that, these research will also serve as a key material to establish and discover advancements in developing large-scale designs for biosorption of the micropollutant diclofenac. More and more methods will be unveiled, leading to the discovery of optimized operating conditions, hence the continuous enhancement of the process performance. Finally, this research will become an area of study to further improve the treatments being made, especially in the extensively contaminated aquatic environments. This study will investigate the adsorption of diclofenac using chitosan-impregnated biochar beads from pineapple crown leaves. Initially, the leaves will be dried, milled, and characterized using FTIR and SEM only. The processed leaves will then be combined with chitosan in a 2% acetic acid solution, followed by infusion in 1 mol per liter of sodium hydroxide and a 24-hour curing period. In assessing the biosorption capacity of the beads, a simulated aqueous solution will then be used across 2 trials, examining the effect of varying temperature, which are 27.5 degrees Celsius, 37.4 degrees Celsius, and 50 degrees Celsius, and biosorbent doses of 2.5 milligrams, 16.75 milligrams, and 15, 50, and 30 milligrams. The biosorption process is characterized using Langmuir and Freundlich isotherms. The slide shows the general flow of our biosorption experiment. We first collected our pineapple crown beads from a local farm in Silang, Cavite and subjected it into a running water in order to perform decontamination and remove the surface impurities. We dried it using a laboratory oven over a 90 degrees Celsius heat for a duration of 24 hours and then pulverized our PCL with a Thomas Wiley mill. We then subjected the pulverized PCL into pyrolyzation on a 300 degrees Celsius heat for 2 hours time. The characterization of pineapple crown leaves was done pre-pyrolization and post-pyrolization. For the preparation of our simulated aqueous solution, we first diluted 40 milligrams of diclofenac in 1 liter of water, and from then we diluted our set of solution ranging from 0 to 14 milligrams with an increment of 5 and evaluated it through the UV-Vis spectrophotometer. After that, we prepared and cured our chitosan-impregnated biochar beads by diluting equal amounts of PCl and chitosan in a 2% acetic acid solution and infused it in our sodium hydroxide solution, creating beads. After that, we utilized a water batch shaker in different temperature settings for the adsorption trials. The investigation of post biosorption and pre biosorption were done using the SEM, and right after, we went straight ahead to analyze our results.
Table 1 is the full factorial design for the removal of diclofenac. QE represents the amount of diclofenac adsorbed per gram of Chitosan-Impregnated Biochar Beads. It is calculated by the given equation. The diclofenac removal percentage is calculated by the initial concentration of diclofenac minus the equilibrium concentration all over the initial concentration multiplied by 100.
The figure shows the pre and post furnace PCl FTIR spectra. However, for us to accurately determine the peaks for both runs, we decided to put the FTIR imaging straight from the FTIR tests. This figure shows that the pre-furnace PCl lacks significant IR absorption peaks, which is likely due to high moisture content or non-polar compounds. However, pyrolyzed PCl exhibits distinct peaks, which are a broad O single bond H stretch peak around 3,200 to 3,400, a C double bond O stretch peak around 1,700, and a C double bond C stretch peak around 1,600, and a C single bond O stretch peak around 1,000 to 1,200. These peaks suggest that the presence of hydroxyl, carbonyl, olefinic, aromatic, and ester, or alcoholic groups. These FTIR results prove that the pyrolysis removes moisture and volatile compounds from PCl, resulting in a more defined IR spectrum. High temperature furnacing likely degrades or degraded complex biomolecules into simpler compounds like aromatic and carbonyl structures, leading to the observed distinct peaks in the furnace PCl spectrum.
The micrograph shows interconnected pores, thus suggesting a porous surface structure of the beads. Its rough texture also appears relatively uniform, indicating that there are no irregularities that could interfere with the adsorption processes.
This figure shows the post-biosorption CIB beads, and it is clearly showing that they are more deformed in structure with less open pores and a less uniform surface compared to the pre-biosorption beads. This suggests the attachment of DCF to the adsorbent surface. The surface morphology of the CIB beads varied across different runs. Runs 3, 5, 8, and 9 showed significant surface changes with large agglomerates and deep crevices, indicating high diclofenac adsorption. Runs 2 and 4 exhibited moderate surface changes with rougher surfaces and partially blocked pores, suggesting moderate adsorption. Runs 1, 6, and 7 showed relatively smooth surfaces with fewer visible pores, indicating lower levels of diclofenac adsorption.
A calibration curve was constructed by measuring the absorbance of standard diclofenac solutions with concentrations ranging from 0 to 40 milligrams per liter. This curve illustrates a direct correlation between diclofenac concentration and absorbance. This calibration curve was used to determine the equilibrium concentration of diclofenac in the adsorption experiments.
This figure shows the experimental result of the influence of temperature on DCF removal. From the graph, there is a clear positive correlation between biosorption temperature and DCF removal efficiency. It can be seen that at 27.5 degrees Celsius, the diclofenac removal is minimal, suggesting that the DCF adsorption with 30 mg per 50 ml of biochar beads is not conducive at lower temperatures. However, noticeable increase were perceived at 37.4 degrees Celsius, which denotes that moderate temperature range can enhance the adsorption process of DCF. At 50 degrees Celsius, the highest diclofenac removal percentage was observed, and the error bars for the data acquired for each temperature overlaps. This suggests that the difference between the two values may not be statistically significant. Therefore, the adsorption of DCF with 30 milligrams or per 50 ml of biochar is more effective in higher temperatures. Similar to the previous figure, the graph in this figure depicts a positive correlation of increasing temperature and adsorption. It can be observed that at 27.5 degrees Celsius, approximately 15% of DCF is removed by 16.75 milligrams of biochar beads. The removal efficiency of DCF significantly improved as the graph presented a clear increase from 15% to 50% at 50 degrees Celsius. One reason that could be attributed for this phenomenon is the increase in kinetic energy. High temperature exposure leads to an increase in kinetic energy that facilitates the diffusion of the diclofenac molecules toward the active sites of the biochar beads, hence enhancing its adsorption capacity. The significant overlap in the error bars for the data acquired at temperature point implies that the measured difference is considered insignificant in statistical view. This supports the previous findings where higher temperature is more beneficial in terms of DCF adsorption using Chitosan-Impregnated Biochar Beads from PCF. The graph illustrated in this figure shows the run for DCF adsorption with 2.5 milligrams per 50 ml of Chitosan-Impregnated Biochar Beads from pineapple leaves in temperatures 27.5, 37.4, and 50 degrees Celsius. Approximately 20% of DCF was removed with a temperature of 27.5 degrees Celsius. At 37.5 degrees Celsius, the removal efficiency increased by 50% and about 60% at 50 degrees Celsius. The continued improvement in diclofenac adsorption efficiency with increasing temperature and decreasing biosorbent dosage suggests that 50 degrees Celsius and 2.5 milligrams per 50 ml represent the optimal conditions for this system. Consistent with the prior two observation, the considerable overlap in the error bars for acquired data points implies that the measured differences may not be statistically discernible.
This graph depicts the effect of biosorbent dosage on diclofenac removal percentage at a constant temperature of 50 degrees Celsius. As illustrated, increasing the biosorbent dosage from 2.5 to 16.75 to 30 milligrams resulted in a decrease in removal efficiency with the corresponding average removal percentages of 58%, 48%, and 34% respectively. This graph depicts the effect of biosorbent dosage on diclofenac removal percentage at a constant temperature of 37.4 degrees Celsius. As illustrated, increasing the biosorbent dosage from 2.5 to 16.75 to 30 milligrams resulted in a decrease of removal efficiency with the corresponding removal percentages of 50, 33, and 26% respectively. This graph depicts the effect of biosorbent dosage on diclofenac removal percentage at a constant temperature of 27.5 degrees Celsius. As illustrated, increasing the biosorbent dosage from 2.5 to 16.75 to 30 milligrams resulted in a decrease in removal efficiency with the corresponding average removal percentages of 20, 14, and 4% respectively. In this figure, the amount of beads and adsorption capacity exhibited a negative correlation. Conversely, a positive correlation was observed between temperature and adsorption capacity, indicating that higher temperatures favored increased diclofenac removal.
The diagram represents the adsorption capacity of the CIB beads for DCF at varying temperatures. It can be perceived from the graph that as equilibrium concentration of DCF increases, the C subscript E over Q subscript E, which is the ratio of the equilibrium concentration of the adsorption capacity, also increases. The R squared value at a temperature of 50 degrees Celsius is 0.985, thus indicating that the model is a good fit for the experimental data. The R squared value of 0.9279 at a temperature of 27.5 degrees Celsius also indicate a good fit. However, at a temperature of 37.4 degrees Celsius, the model exhibited a moderate fit to the experimental data as indicated by an R squared value of 0.8554.
This figure illustrates the linearized equation of the Freundlich isotherm by plotting the log of the equilibrium concentration versus the log of the adsorption capacity. The isotherm showed a negative slope indicating that the beads deviated from the expected behavior. Despite this, the R-squared values of each temperature were all a good fit. In summary, the R-squared values of both models fit the data well. Langmuir was more suitable at higher temperatures and Freundlich was better at lower temperatures. These insights can inform the development of efficient wastewater treatment strategies using CIB beads. Chitosan-impregnated biochar beads derived from pineapple crown leaves were synthesized to investigate their potential for removing diclofenac from water. Batch experiments were conducted to evaluate the effects of temperature and biosorbent dosage. Higher temperatures enhanced diclofenac removal, likely due to increased kinetic energy facilitating diffusion. In contrast, increasing the biosorbent dosage led to decreased removal efficiency, suggesting a saturation point where additional adsorbent does not significantly improve adsorption capacity. Overall, this study demonstrates the potential of Chitosan-impregnated biochar beads as an effective adsorbent for removing diclofenac from water bodies.
For this study, we have a few recommendations. We recommend to prolong the drying time for improved physical properties of the beads, and we also recommend to immediately mill the dried PCL in order to achieve a more consistent particle size. We also recommend an automated steering or magnetic steering for uniform biochar bead mixture and increased yield. And we would also like to recommend using a wider range of isotherm models for deeper adsorption mechanism insights. Exploring continuous flow systems for real-world performance and scale-up potential is also recommended.